Good morning, everyone.
Morning, sir.
Morning. I'm having a little bit problem from my computer, so let me log in. Can't log in into Fab. All right, there we go. Share my screen. Freezing. Chapter 1. There we go. So could you quickly remind me where exactly we left on Friday? Any of you? I'm scrolling down. Take a look at your computer. You may remember.
Nine.
Right here, components.
Yes.
Okay. So we'll talk about components and hopefully we can get to the end of it today. My Fab, I can't log in. What happened? Oh, by the way, I have put a deadline for your labs. I think if you go to LMS, you'll see it is October 10th of October. Today is 13th of September, so almost 4 weeks, a month you have. Okay. But that doesn't mean that you'll be leaving that one for the last moment. You should try to do it as early as possible, as I said, because over time you will have some other courses, and all these courses will have respective materials, resources, the assignments that you will have to do. So right at the beginning, that's my purpose. That's why I opened it. And I want all of you to wrap it up, finish it off as quickly as possible. So that is the reason I have given you, I think 1 month is more than enough time to do it, but do it as early as possible. All right, if you have any queries as usual, just let me know and we will try to fix it together. Many of you, as I said, as a reminder, you will have problems during installation. Nothing to worry. Try one or two more times. If you see that it's nearly not working, the problem could be coming from your underlying hardware. It's normal underlying hardware or kind of conflict between your OS and the virtual machine and new OS that you're going to install on top of it. So if that is the case, then let me know. Rather than freezing, rather than stopping doing it, just immediately let me know by email that you are having a problem. So I will give you a walk around. And maybe we can do something online. So no problem. I will not penalize you for that failure. But that failure must be well documented. The documentation is the key, as I mentioned. Everything must be properly documented. That's the main objective of these courses, of these labs. As its purpose is to give you a hands-on experience to see how your OS responds to user commands. Now, in reality, you are not supposed to, in today's context, in older times, we used to use these commands, as I told you, MS-DOS. But in today's computing environment, you are not supposed to interact directly with your underlying OS. But these are the things that your apps or your softwares are doing. Right. So that's why I said that the purpose of the lab is just to give you hands on feel of how you do it. But please do it. Don't forget to submit. Don't miss the deadline. If you do it, you get 0. And once you get 0, you can't go for the final exam. That's for sure. All right. Now let me see. Well, we'll get started right here. As you can see, we'll start talking about operating systems. In the meantime, once more, go there and check your labs. So I've set up a deadline. All right, there we are. So let's get started with a concept that we're talking about. This is the last part of it. Now, as I say in the concept, the things that we are going to study are the same things that we'll be repeating in the subsequent chapters. So we have altogether 5 more chapters to go through, and these are the things that we'll be studying right there. First, process management. We'll raise some questions. One of the fundamental things that we'll be studying is how these processes, of course, we will get to know processes in more details, the process behavior, the process attributes, the way the kernel intervenes in modern interactive computing environment to switch the processes. That's another thing we'll be learning in chapter 2. So sorry. So this is what we will study in chapter 2. This is chapter 3. This one and this one together, chapter 4. This is chapter 5. And also related to process management, as we understand the situation inside our interactive computing environment, multiple processes are trying to access multiple resources at the same time. So naturally, but in terms of execution environment, execution scenario, only one process at any point of time can use one single resource. And that creates a conflict all the time, especially when you are trying to share those resources among multiple processes which keep asking for those resources. But only one of these processes can use that resource at any given point of time. So of course, these are all managed by OS, or rather the kernel of the OS. Okay, that's why we called it the controller or the manager. Control and coordinate. So everything is being coordinated by the resource manager, which is the operating system. But to stay safe, we use two important things, important concepts, and these are the ones that you're looking at right here, IPC. This is the most end process synchronization. We start through process synchronization. I will let you know that what synchronization is all about. Synchronization is, if you think about this is the shared resource, and there's a multiple processes trying to access this one. This is P1, this is P2, and this is P3. So essentially, what we expect is we have to synchronize how they access these shared resource. That means when P1 is right here, P2 should still be waiting. P2 can't step in to that resource until P1 has fully left or released that particular resource. In case of any overlap, there will be a deadlock. That's what we'll be looking at in chapter 6. This is chapter 6. That is deadlock. Sorry. So that's what we'll be looking at. And also, we'll be learning about IPC, which is an important chapter, very interesting, and that is inter-process communication. Okay, inter-process communication, that is what you'll be looking at the same time. Now, moving on, they're talking about the process hierarchy, which is not an important thing, and we're not going to study it in much detail today. Pipeline, process hierarchy and pipelining, that means two processes interacting with the runtime being facilitated. This interaction is being facilitated by the underlying operating system. That is a concept that we don't use so much in these days in modern OS. But, well, I shouldn't use the word modern because just maybe 20 years ago, when Unix we were using 20 or 30 years ago when we were using uh, the Unix platform, these things were supported. These things were primarily Unix featured, right? So we will see. We will get to see it in brief, as to keep it as simple as possible. This is the scenario that we will discuss in more details when we go to chapter 6. As we can see, talking about deadlock, just now I mentioned, it all happens because multiple processes are trying to access multiple resources at the same point of time. Now, when it comes to the request, there are two different scenarios. One is the request scenario, and one is the actual execution scenario. In the request scenario, multiple processes are allowed to request multiple resources. It's a kind of many-to-many relationships. If any of you know about this term in database management systems, you'll find it many-to-many relations. But when it comes to execution scenario, it's strictly one-on-one. That means one process can use one resource at a time. And even just in case the overlap, they will run into deadlock. So there are three ways to address this issue. And OS will get involved when IPC and synchronization fails. Remember, we talked about IPC, inter-process communication. We talked about synchronization of process. So if these two things fail, then we definitively run into a deadlock situation. And OS, your operating system, especially the modern operating system, has an important role to play to try to mitigate the possibility of two processes getting involved in a deadlock, even worse still, a fatal deadlock that kills the computer. Okay. So that is what we'll be studying. So three things, three ways it can intervene. It can try to prevent. Now, prevention means applying some kind of brute force to prevent it from happening. We'll see all these things in more detail in chapter 6, and we'll have a handful of wonderful algorithms. Another way of dealing with this potential deadlock is avoidance through prediction. But there's a difference between avoidance and prevention. Prevention, as I said, is more like applying a brute force to prevent it from happening. Avoidance is a logical solution. Avoidance is where we try to predict it. And now, as I use the word prediction, you understand to predict something correctly, you have to think in a logical way. And yes, for that, we have a wonderful algorithm, a very, very important algorithm. Trust me, you'll get a question. You will get one or two questions in your exam from that algorithm. The name of the algorithm is called Banker's algorithm. So we will talk about it in chapter 6. But we apply those algorithms, or rather OS applies those algorithms to stay safe. Okay. Now, if these two things fail, if it fails to avoid, it fails to prevent, then obviously we run into deadlock. And as we run into deadlock, then there must be a strategy for the OS to somehow recover from that deadlock situation. So we'll talk about prevention, we'll talk about avoidance, we will also talk about the strategies we may apply to try to recover from the deadlock. It's not always possible, though. It's not always possible. And in fact, we'll get to know that why it is not possible, in spite of having this wonderful Banker's algorithm. It's not always possible to avoid it. Right. Why deadlock happens, we understand. A set of blocked processes, each holding a resource and waiting to acquire a resource held by another process in the set. Obvious. Main memory, when we go to that chapter, it will be primarily dealing with two aspects of memory management, starting from the early days of multi-programming. That is, the increase system performance and maximize memory utilization. The key thing to remember here is, as we discussed a little bit earlier in the hardware chapter, the same thing, that the RAM is limited memory space. It's not possible to expand the RAM. But the way your hard disk is expanded, that means hard disk could be anything like 20 GB or 30 GB. But when it comes to 20 GB or 30 GB, but when it comes to your RAM has limited space, limited operational space, right? And you can't just keep expanding RAM in your own switch will. It's not possible. And we know why, because it needs to be compatible with the CPU that is supporting the RAM. Without the CPU support. And this is a common scenario. Like when we go to buy a new laptop, we ask the guy in the shop, what's the RAM for this laptop? He might say, well, it's currently 4 GB, but you can extend it to to up to 6 GB. When you hear that answer, you wonder that if I can extend the RAM to 6 GB, why not to 8 GB? Why not to 10 GB? The obvious reason is that CPU, the processor, will not support the RAM. So there you are. First of all, we already know that it is more expensive because it's a volatile memory, high-speed volatile memory compared to hard disk. But on top of that, it needs the support from the underlying processor, the CPU. In fact, the CPU must be able to generate enough address space for that RAM. If the CPU can't, then definitely your RAM will not work with that particular CPU. And changing a CPU literally means buying a new computer. There's no point doing that. And that is what we were doing in that part. And then we're dealing with that one, how we can do all these things. Finally, we will move on to memory management. In memory management, as we can see, in memory management, the real motivation, from the memory management, we move on to file systems. Now, I'm not sure if I asked that question. I feel tempted. Early in the morning, I just wanted to ask that question to you. What is a file and what is a directory? Okay, I give you the answer. Because remember, when I ask this question to most of my students, and I get an answer which is correct, as long as you are just an user, from the user point of view. But from a computer engineer's point of view, or from the system's point of view, the definition is not right. For example, I got some answers on Friday when I asked this question. Students now, they say a file is where we store information and data. No, we don't. You shouldn't be using the word store. That's the answer that an user will give. But from a technical point of view, a file is an abstraction of behavior and data grouped together. Now, I give you a very simple example. It may sound pretty silly, but that's what it is. Now, you know that you have a file saved on your desktop folder. Okay, and it's saved on your desktop folder. And the desktop folder. And now, since you have that one saved on your desktop folder, you want to get the file, or maybe you saw an important file in your friend's desktop and you said, hey, I want to steal the file. So what you do, that you take his hard disk out and run away and break it open. As you, oh, sorry, that's my little daughter. All right. So the thing that Sorry for the interruption. So talking about the file systems that we have, but we're talking about file and directory. So what's a file? A file is something So that's what we said, the file system, and talking about the files, because the files, in fact, if you want to have the files, these files are nothing but abstraction. The one that I was talking about, that when you break it open and you say that, okay, I can find the desktop and I can find the file, but can you really do that? No, we can't. That's a ridiculous idea because we can't exactly know exactly where the file is. In fact, the file is not stored, the information or the data of that file is not stored in one place on the hard disk. Okay. They have been kind of split up into small chunks of byte blocks, and these byte blocks randomly dumped everywhere, all over your hard disk. Okay. So that is exactly how it works. Directory, on the other hand, we ask the question, what's a directory? Now, directory in modern times, those who are aware of that, it was a directory is a folder. And what is a folder? A folder is a storage. No, it's not a storage. It is just a list file that lists out all the items that you are storing. And for each item, it stores a handful of metadata. If any of you are aware of this word called metadata. Metadata means some specific information about the file, some attributes of the file. For example, the extension of the file and the size of the file, and then who created the author of the file and the date when it was created, that file. So we have all these information noted down right in there. Okay. So that is what we call the file directory. So that's a flat file, it's a list file. So that is more like having a morning shopping list and evening shopping list. That doesn't mean that your items are actually inside the list, but you are listing it out. And when you want to change, when you change your mind, you don't want to put something in the morning list, so you cut it and paste it. But it actually, where are the data of those files? When you are cutting and pasting them, are you are you changing the position of the actual data byte blocks? No, we are not doing it. So we are not doing it, and we are just moving the links from one directory to another directory. It's a system file that helps you to organize your works in the format of a list. Okay. Isn't it? Now, moving on. Moving on, this is what directory is. Directory is all about. This is all what we call a directory. And as you can see, now, generally looking at this one, you'll be saying that this is folder, isn't it? Yes, it is a folder. These are all folders. That's why I say the directory, we don't use that more these days. But remember, in this book, especially in that file system chapter, we never use the word folder, because folder is a wonderful illusion that's been created to deceive the users. In fact, for good, to make things more user-friendly, isn't it? You have the perception that you're actually using something where you can store your files. So that's not the case. But anyway, need to be technically perfect, because these are not folders, these are directories. When we go to the I/O management, we have two different parts. One part that we already discussed a little bit in the previous part, in the hardware part, that is this hardware, I/O hardware. And then we also have I/O software, and the softwares are more important. The softwares, without this software, the hardware will not work. Right. And that's what we will talk about. Talking about hardware, software, starting from driver. Then we have the interrupt handler. And then one of the most important I/O software layer that we have, that's part of the OS, in fact. Device driver is not part of the OS, right? We understand that. The driver is a third-party software installed there. But one thing that is part of the OS and its responsibility is to do whatever it needs to be done to manage this I/O or input-output activities, is a device-independent I/O software layer or input-output software layer. It does so many vital jobs. Okay. And some of the things that they have mentioned right there, caching, buffering, spooling, we will learn about these things, this I/O software in details. Then secondary storage management is volatile into small data, all the data. Secondary storage devices, magnetic disk and optical disk. We will learn a little bit about disk scheduling and disk space. And for disk space management, hard disk, we already know something that we discussed earlier. It's all about mapping, logical interpretation of the physical space. And that these are things that we'll be looking at. Right. Once we cover these parts, then we go to protection and security. We will not have a chapter on this, although in your book you have a chapter. If you're interested, you can actually study that chapter. In fact, give a presentation later on from that chapter. It's called Security, Chapter 9. But we are not going to study it in details. Right, it's not part of the syllabus, your final exam syllabus. Moving on, there are quite a few things. So when I'm here in protection and security, I feel that I should ask you this simple question. Now, the two words that we hear quite often is these two words are authentication and authorization. Can anyone tell me, are the same or the different? Or in fact, I can put it in a more simple way that if every day you log into your websites and portals and apps, you log in everywhere. Like wherever you go, you need to put your ID and your password. Now, when you use ID and password login to your account on any device, at any portal, on any website, any app, what are you doing? Are you authenticating or are you authorizing? Or do they go together? Do they go together? Authorization and authentication, or they're kind of independent of each other. So, what is your take on that?
Well, I think when we're logging in, we're doing authentication.
So, there's no authorization involved there.
Yeah, because of the authorization means like you're identifying what you can access to.
Okay, that's key. So, basically, authentication and authorization they go hand in hand, they go together. For example, both you and me, both of us, we can use our APT email and our individual passwords to log into LMS. But once we authenticate, when we give the ID and the corresponding password, we prove who we claim we are. Okay. Basically, when I put my password and the ID, that's the email, then I prove that I am who I claim to be. That is authentication. But then, so the system allows me to step in. But immediately after stepping in, they will also verify my ID to check if I'm a teacher or a student. If I'm a teacher, I will be given some privileged access. That means I can access some of the things on LMS which, as a student, you can't access. For example, the question bank. Right. That is authorization because I'm authorized as a teacher, I'm authorized to access those resources, which you are not because you are a student. So basically, wherever you go, authentication and authorization, they go hand in hand. That's what they will be talking about right there. They're also talking about the user interface. Almost all operating system has the user interface, a UI, command line, graphic user interface. Today we'll use the graphic user interface and a few other things related to IO device like keyboard, mouse, how do they work. We'll keep it as short as possible, but yes, those are also there as part of our syllabus. We will study it. Communications, change, exchange information on the same computer or between computers or a network. Error detection always needs to be constantly aware of possible errors. Okay, and they address these issues very well. Now, talking about system calls, it in itself it is quite a complex thing because the system call, as we know, is all about a track, a service request, and the service request must be coming from one of the apps which is running the user mode, and they need a service from the underlying hardware. And whenever you need a service from the underlying hardware, it will generate a trap to the kernel by changing the mode bit. You can still remember the kernel's mode bit was 0 and the user mode's mode bit was 1. So the mode bit needs to be switched from 1 to 0 to pass the control to the kernel code so that kernel pays attention and kernel takes it out to does whatever it has to do to get in touch with the underlying hardware component and generate a response. Once it gets a response from the hardware, it needs to feed the response back to the user mode, and that we do by switching the control or switching the mode bit once more. Right. Now, that's a complex process. You don't have to go into much details of exactly how system calls are executed. There are 11 steps there. That's what 11 steps. But I would rather focus, for your exam's point of view, would rather focus on some of the key things, like key commands. In fact, many of these commands you'll be using for your labs, lab 2, 3, and 4. Lab 1 is all about installation, lab 2, 3, 4, all about writing commands. And I reckon if I can remember properly, lab 4, you will even have to write a shell program, a very basic shell program for the Fibonacci number. Okay. So if all the instructions are there, by the way. So see how it's executed. When you write a C program, is you write printf, but printf will be converted to write. Now, printf is something that the user mode will understand, and it will go through a standard C library, and the C library will eventually, for the kernel, it will give a write call. Write is the system call. So if you were trying to perform the same task with printf through a kernel, to a shell, directly interacting with the underlying OS, you better type write, because there you are talking to the kernel and you are bypassing the user mode. But if you want to come through the user mode, then the standard code is printf, because it will go to the standard C library and we know exactly what it means. It means, in terms of system call, write. And these are some of the things that you'll be needing from now on to pay attention to. They've given quite a few of them. In fact, strongly recommend that you can practice at least 1 or 2 times. Like you Google, and you'll find all the Windows shell commands, okay, and write it. Open your command prompt, Windows command prompt, and give those system calls. And then later, when you install Fedora, go ahead. I've shared, you can see on that LMS, in the lab section, I've shared a link where you can find all the Linux bash commands and their details. Okay, so go there, try it, and see what response you get. Okay. You have to follow the syntax. They've given all the details right there. It's good to just run the commands from the shell. They've given lots of commands. It's a program. It's the kind of program that you'll be writing on lab 4, the Fibonacci number. And that's what we call shell programming. You not only pass a command, but on the shell, you can write a program. You can write it separately in a .sh file and load it on the shell and run it, or you can run it straight on the shell, no problem. One important thing that this particular picture shows is structure of a standard program, when it's loaded in contiguous memory spaces on RAM, it gets split up in three parts, three important parts. One is program, one is data. Now, we also have a stack, and we also have lots of other things which are part of the programs. So we have a program that is what we call text, which is basically the instructions, the codes, and then top of that we have the data. Usually, the data layer is pretty thin. The data part is more like when the program gets loaded. Right at the beginning, we declare all the variables. For example, integer x or integer xy, an integer array of length 10 with a name. Now, we create some space holders. This is what we call this placeholders. Placeholder means when you declare an integer array of length 10, that means uh, your compiler or your machine, your CPU, will actually reserve, while it's getting loaded, it will reserve 2 bytes, right? One integer, 2 bytes. 2 bytes into 10, 20 bytes. So 20 bytes of space. So that is why we have a data sector. But over time, that data sector will keep growing. So the data will keep growing and growing. Okay, so that is what happens when you load it right on RAM. And then we have a stack because the concept is we don't execute all the codes at the same point of time. Rather than that, each of these things will just come and go, so one at a time. And that is what we do. From the stack, we start executing them one by one. Okay? So that is what we do in there. The interesting thing is a program a program keeps growing when it's running on RAM. It keeps asking for more space. And this will be our challenge to deal with because a program, while it is running, can be a program can be asking for more space. So that is what it does. So this to deal with that situation, what we do is to give a little bit of gap, a little bit of space, because the stack keeps moving downward while this uh, data part keeps moving upward. Okay. So that makes the difference. We're looking for the moving machine. They're talking about the system calls and how it weighs. These are some of the things that you don't have to pay too much attention to. It will just pass by. And all right, now moving on to the next one. This is one of the charts that you might like to remember, because that is what we call the system call chart. The chart of the system calls, and they have given in much details what we do, each of the systems, and then how they do it. This is Unix and Windows 32. They have different commands. The last part of it is all about structure, and if we can finish it earlier, then we will move on to some more serious study with the next chapter. The operating system monolithic structure. The monolithic system, layered system, virtual machine, client server models, and microkernels. We are already familiar with these words, but just a quick look at what these things stand for. Monolithic system, as I mentioned, as an example was MS-DOS, where everything was written in a bunch of procedures. So everything was pretty procedural. Right, and that is what monolithic system was all about. Perfect example was MS-DOS. When it came to the market, it was just a kernel that was given. Okay. The others, just a kernel, no user mode. And everything that you'll have to do, everything with a shell, or rather an interface, command line interface. If you want to interact with it, you will have to send these emails straight away. You have to write, you have to interact with. You are supposed to interact directly with the underlying kernel, the utility procedures. So everything but these procedures were arranged in three layers: the main procedure, service procedure, and utility procedure, as a simple structuring model of the monolithic system. But the one thing it didn't do, didn't organize these codes, these kernel codes, into multiple modules. The structure of the operating system in the monolithic structure, a main program that invokes the requested service procedures, a set of service procedures that carry out the system calls, a set of utility procedures that help the service procedures. So just everything procedural, but no separation of codes. For example, in modern OS, we're talking about file systems, a module that takes care of specific interactions with a hard disk. But that kind of separation was not there in the monolithic structure. And of course, there's nothing called user mode. As you can see, the MS-DOS written to provide the most functionality in the least space. Now divide the modules of the MS-DOS as some structures, these interfaces and levels of functionalities are not well separated. A very common question that you will get in the exam that we used to ask is, MS-DOS is a monolithic structure, or which of the following is an example of a monolithic operating system? So be careful for that kind of questions. In fact, after we dealt with the monolithic system, we moved to the layered system. Now, remember, in between monolithic system and layered system, that is MS-DOS, and this is Vista, that is when Microsoft launched its layered system. We had almost 20 years. And these 20 years, it was the era of Windows evolution. Now, Windows basically was running DOS behind the scene and had added a beautiful user mode. And of course, from time to time, some key enhancements in terms of technicality, functionalities, and other things. So that's what they were doing. Around 2000, Microsoft decided to change it and introduce the layered system, which was, for some reason, an utter failure in the market. But that was Windows Vista for the first time. What they did put it down. This is important for you, this particular slide. The layered system, how many layers are there? 6 layers. Okay. As you can see, the bottom one is a core to the kernel. Then each layer was split out in a separate way. Now they belong to different layers. In the Windows OS, they were in fact part of the kernel itself. But here, instead of having one kernel, we are putting them separately in separate layers. The simple, obvious reason for doing it was the maintenance. So that means Microsoft can maintain this huge software. Vista was really a huge software. Okay, you need at least 2 GB of RAM to install Vista. But then they introduced it and expected that it will succeed after their XP, which was really a big success in the market. But it was slow. From the user's point of view, it was definitely slow. So it didn't really click. Since it didn't click, they had to move on to 2003 and some other versions. All right. Moving on, after this one, we introduced a concept. This is the virtual machine. Now, this is something that you'll be dealing with. Okay. It's good to look at the structure of the virtual machine because virtual 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 machine, the key difference between one single machine and the virtual machine is the virtual machine is where you have the most important thing about when you install a virtual machine is a virtual machine implementation layer, sometimes called a hypervisor. And these hypervisors or virtual machine implementation layers are the key players because whichever virtual machine is in action, you can actually install multiple virtual machines and you can run multiple operating systems on each of them, as you can see, and it's technically possible. Okay. Then it's the hypervisor or the virtual machine implementation layer that will be responsible for dealing with this, dealing with the underlying hardware. It's a layered approach to its logical end, logical conclusion. Right? It treats hardware and the operating system, the hardware and operating system kernel as though they were all hardware. A virtual machine provides an interface identical to the underlying bare hardware. The operating system creates the illusion of multiple processes, each executing on its own processor with its own virtual memory. So it is an illusion that is created, and that's the way they execute it and they do it. Okay. So that's how these things play out. You don't have to go into details of these, but all you need to know, need to remember is this one's some of the names and where we use it and how we use it. The resource of the physical computers is shared to create the virtual machines. Right. So that is also.
But I'm reading on my chopstick. You want chopstick? Are you sure? Because now you tell me that you need a spoon, now you need a chopstick. Already?
That's good. Spooling is another. Spooling in a file system can provide virtual card readers and virtual line printers. The normal user time sharing terminal serves as a virtual machine operator console. There's a whole bunch of things right in there. Microkernel. I think we saw this picture before. What is microkernel about? Microkernel, the client server model. Well, client server model is where they introduce the microkernel. Now, as I said, that we introduce microkernel because the microkernel is a high-speed hardware. That means we keep the kernel as minimum as possible, right? So that is why we call it microkernels. You can see there are multiple kernels, and for each of these servers, and they're connected to a native client model in distributed system and in the one single server model. One single server model, there's no way you have to keep a microkernel to gain on speed. Microkernel, that is what you're looking at. It is all about kernel to microkernel. The operating system is divided into microkernels. Now, moves as much from the kernel into user space, and communication takes place between user modules using message busing. In other words, in theory, as I said, it is all about minimum kernel. the lightweight kernel. Because if you keep the kernel loaded with lots of codes, you're asking for slowing down the machine. But that's what we need to avoid, especially when we apply the solver. There's something called matrix unit, and as you look at it, that is, I think we already know what is KB, MB, EB, GB, TB, PB, EB, ZB, and YOB, YOTA. Okay, we talked about that. Now that is how we're needing these metric units when we don't have to go that far there. But anyway, good to know. So that brings us to the end of these the so-called introduction of this chapter, which is kind of like an overview of the rest of the things that we are going to study. Right. So we'll move on to our first important chapter, that is the chapter 2, where in chapter 2 we'll be dealing with process. And that is the chapter 2 that we'll be dealing with. So let me try to find it out. Must be somewhere. Read processes. Okay. So let's see what we have in store. It is opening. This concept. Okay, processes and threads. Let's get loaded. So we are now entering chapter 2, that is processes and threads. Processes and threads. So what do we have in the process and threads? A little bit of understanding. These are the objectives that we'll be going through. Definition, the process model, process creation, process hierarchies, process termination, process states, transition state, implementation of process, and degree of multi-programming. So these are the things that we are going to study right here. These are the things that we are going to study right here. So how do we do that? Let's move in and take a first look. As you can see, as I said, that these are my teaching slides, and in the teaching slides you will see everything you will find in your study slides, the old study slides, but pay attention to all the highlights that you can see right in here. Right. The OS abstraction. Some of the key words, as you can see, I have highlighted. Now, what is a process? A very interesting word. And we'll go slow at this stage. Don't worry, we have plenty of time. But some of the key things that I want you to remember from this particular chapter is about, for example, the abstraction. Get familiar with this word. Okay, you'll be getting the word abstraction everywhere. In fact, even even when you go to deal with uh, Java, because you guys are learning Java probably, you're not sure. But if you want to learn Java, then you will have abstraction there as well. Now, abstraction is what we call adding some layers of indirection. Yes, by definition, that's what we mean. Now, in this case, abstraction is everywhere inside computer science. So OS abstraction to support the ability to have pseudo-concurrent operation even when there's only one CPU available. So it's an abstraction. Why we call it an abstraction? Because we understand what a process is. A process is a bunch of programming codes, right? Now, but it's a transition that the programming codes go through. That means you have the programming codes, and when you want the programming codes to get loaded on RAM and start running, it goes through a transition. And this transition is what we yes, and the point is that these abstraction that we look at, that when uh, a program gets converted to a process, it's all about a whole bunch of new things are added to it. Okay. So that is how these things work. Number two that we have right here, I just first let me introduce the highlighted words, the concurrent operation. We already know that they work together, like on single CPU, but multiple processes are running side by side. And that is what we call concurrent operation. Okay. So that is what we are having right in there.
The top one.
So that's what we call concurrent operation. Next thing is about switching the process CPU between processes, because that's what it is doing. It is literally switching it from switching the CPU, and that in fact has a word that is called context switching, and it keeps context switching from one process to another process, right? And an instance of an executing program, including the current values of PC, register, and variables. And in fact, that is how we defined it as an abstraction. Okay. A process is not a program on disk. A process is not a program on disk. It's a program that is just a file. A program on a disk is just a file, but a process is, as we said, is an abstraction where we add all sorts of extra things to make it work. It's a sequential stream of execution in its own address space. Of all the different types of definitions that they have tried to give here, for a process, I'd rather go for the last one. But to understand what it means, you need to understand the concept of address space, which we will discuss in the next few slides. Now, everything, this is also another abstraction. It's also another logical thing, right? And maybe some of you already know what address space is all about. The point is, a process is a sequential stream of execution in its own address space. And that's the way it must work. So that's why we call it an abstraction, first of all. We also clarified that these processes in modern computers running one CPU get switched all the time. Okay, from this to that, this to that. And number 3 is that it is these processes, they're constantly switching the CPU among them. It's a whole bunch of, that's what we call abstraction, a whole bunch of things attached to the programming codes. That means in real time, it now has a PC value and all the registers values and the variables. It's not a program. Program is a kind of text file. But in other words, sometimes in some way you might see that people say that it is a process. A process is an active entity, whereas the program is inactive. Okay. Now, a process is a sequential stream of execution in the address space, in its own address space. Each program will be given an address space. And these address spaces, they are given to a program because whenever a program is installed and the program registers itself as a process, it will have to get back to the CPU, and what the CPU will do is basically give it a little bit of address. And a little bit of address, and these addresses are very, very important for it because these are the addresses that CPU will maintain in its register. And based on these addresses, later CPU will be executing the codes in a sequential way. So what is an address space? An address space, to keep it simple, is that the program, the entire program that you have, the CPU will map the entire program. Will do a few things when the first time the program registers the process. Only one time, the very first time. First of all, each line of code inside that program will be given a logical address that usually starts from 0. It always starts, right? I should say, always starts from 0 up to a maximum value that a CPU can generate for the RAM. And that is where a RAM and CPU they become dependent on each other. The maximum value that CPU can generate. Okay. So that is exactly what CPU will do. So CPU will generate address starting from 0. So now, and remember, these are all logical addresses. And after generating those addresses, in fact, all these programming codes that you have inside a program now will have their own address. So at any point of time, if CPU wants to access a particular line of code, all it has to do is know exactly where to go to find it, because it has an, the entire program mapped in a logical way and in an address space, and this address space is in the hand of the CPU. Okay. So that is what a CPU does right at the beginning. But now when you have a whole bunch of address space in front of you and you want to execute it on RAM, you put it on RAM and start your execution, and you quickly know exactly which line you are executing at this very moment. All right, we'll leave it here because we need time for your attendance. And we'll get back and again get started right from the beginning of the process. Okay. So in the next class, when I ask you where to get started, remind me, we'll get started right from the beginning of the process. Chapter 2. We'll have further discussion in this part, because these parts are very important and interesting. A lot of keywords, as you can see, all highlighted. Those were notes which will help you to take notes on this particular part. Take your attendance as quickly as Ji Kang, Vin Phuc, Duc Huang,
Yes, I'm here.
Lung Ha,
Yes.
Hu Huang,
Yes.
Tan Hung,
Yes.
Nop Phat,
Yes.
Din Min,
Yes.
Quoc Huy,
Yes.
Yan,
Yes.
Kim Thak,
Yes.
Nyat Min,
Yes.
Yen Phuc,
Yes.
Quang Huy,
Yes.
Min Quong,
Yes.
Duy Bao,
Yes.
Huy Min, Liêm Chúc,
Yes.
Quoc Hung.
Yes.
Once more, those who are absent, Vin Phuc, Chi Kang,
Yes. Yes.
and Xuan Huang.
Yes, teacher.
Okay. So only Vin Phuc. Let's check. All right. Thank you, and we will see you again on Wednesday. We'll start with chapter 2. In the meantime, pay attention. Your lab is open. Go through it.